separation logic at some level. So we are looking at foundations of what we call natural proofs and also this other heuristic called quantifier instantiation. Both are heuristics to deal with quantified logics or logics with recursive definitions. And this is joint work with Christof Löding at Aachen and Peña at Illinois. So the setting is similar to the previous talk. We wanted logics for automated deductive verification, where we are taking a program, annotating it with pre-post conditions and loop invariants, and trying to generate verification conditions from that, and proving using a logical engine that the verification conditions are valid. Right. So which logic do we use? Right. The most for automation, the most standard one is quantifier-free logics with lots of background theories because they're combinable using Nelson-Open and they're typically decidable. So this is the most popular one for automation. Of course, you have other logics. You could use first-order logic. You could use first-order logic with background theories like arithmetic and so on. Or you can use first-order logic with least fixed point, which is my favorite logic, right? Which is because you need really least fixed point to talk about recursive definitions, semantics of recursive definitions, and objects like linked lists and so on. Okay, so we need quantified logics first. So because we always have unbounded parts of the program state that we need to model, arrays, data structures, and so on. And also to express in any real verification task, you really have a lot of ghost state and spec state, like sequences, sets, and so on, that you're trying to refine, right, into code, and you need quantified logic. But quantified logics are typically undecidable. So the key thing here to note is that automation is the requirement, right, not really decidability. And the question is, can we build automated logic solvers? And so one way is to look for decidable logics. You can take the logic that you have and identify some sublogic, which is decidable, and that's the usual way people proceed. And it has lots of advantages. It's predictable. You know it's going to say yes or no, given enough time, and it's going to give you counterexamples. If the answer is that it's not valid, then you'll get counterexamples. And typically the disadvantages are the sublogics get more and more awkward. As we try to make the logic more and more expressive, the logics get more awkward, and also the proofs get very complex. So I've worked in this area for a long time, and I kind of moved away because the proofs get really complex that they don't really work in practice. So what I've been proposing for a long time is now what is called natural proofs, right? Where the idea is to take a formula, not to restrict the logic in any way, take a formula in the logic, right? And instead of deciding it, what we do is we enumerate certain formulas from this formula, phi1, phi2, and so on, which are sound abstractions of the formula psi. So that if any of these, if phi1 is valid, then psi is valid, and we can stop. Otherwise, we move to phi2, which is larger, right? And we look at phi2. If it's valid, we stop, right? Any of these, if they're valid, then psi is valid. So think of it as an abstraction of the original formula. But the advantages are, of course, the logic is expressive. You can express what you want. The proofs tend to be simple because, well, the simplicity is really in this natural, in the way you enumerate this, right? If the abstraction is good, then the proofs tend to be simple. And these formulas are decidable logics, and typically the way we have designed them, engineered them, is to have it in SMT decidable theories. And in this work, we're going to show that it's sometimes complete as well. That is, if psi is valid, you're going to definitely find some I at which point phi I is valid. Okay, so this will become a recursively enumerable procedure. So what are these two heuristics? One is systematic formula-driven quantifier instantiation, which is quite popular in SMT solvers. The idea is that if you have a formula of this kind, which with quantification, then you instantiate the variables using terms that are already present in the formula, right? And this instantiation gives you new terms, right? Because you can have f of x, and if you replace x with g of y, then you'll get f of g of y, and so on. So you have to rinse and repeat till you get more and more complex formulas, right? But these will all be quantifier free, and therefore amenable to automated methods. So formula-driven quantifier instantiation is quite a common heuristic, and it's been long known to work well. So the other work is natural proofs. which is a sequence of papers we've written, which are basically heuristics that mimic how people prove formulas. For example, and the idea is to handle first-order logic with recursive definitions, which have least fixed point semantics, as well as background theories. And these kind of logics are strong enough to express many separation logics, and we in particular this logic called triad, right? And we can express this using purely first-order logic with least fixed points, right, and a background theory. For example, this is a definition of a list, and the heaplets are defined using a background theory of sets. So the heuristics are basically unfolding recursive definitions, which happen in manual proofs as well. And then after you unfold recursive definitions some number of times, you can interpret the recursive definitions as uninterpreted functions. And clearly that's a sound abstraction. If it holds for any uninterpreted function, it clearly holds for that recursive definition as well. Now the resulting formulas will become decidable, and moreover, because these are quantifier free, you will solve them using SMT solvers. All right. So now natural proofs work very well in practice, so that's what we've been showing, right? But they also fail on very simple things, right? So if you take this one, they actually are not able to prove. And in general, anything which requires a non-trivial induction will not be able to prove, right? But once you give these kinds of axioms, it performs incredibly well and is very robust and fast. So the first thing I want to note is that natural proofs, which is the unfolding recursive definitions, and quantifier instantiation are actually very similar, right? Because when you unfold this definition, for instance, right, this is similar to replacing x with next of x, which is just a quantifier instantiation. So this is why we kind of look at both in the same breath here in the same framework. So the questions we ask are, why do natural proofs work so well when they do, and why do they fail so miserably when they don't, right? And are natural proofs in any sense complete, right? Because if we unfolded definitions for longer and longer time, will we always be able to prove every theorem? And if not, when are they complete? Okay, so the main contributions are to show that first of all, for pure first-order logic with no background theories or no recursive definitions, systematic term instantiation is complete. This is kind of known. I wouldn't say it's a new result. The second one is the main result, which is for first-order logic with background theories, systematic term instantiation of what I would call the foreground logic sort is incomplete, but it is complete for a safe fragment. So there is one fragment which is fairly natural, for which the instantiation is complete. And this explains why natural proofs actually work well in practice. And finally, first-order logic with recursive definitions and background theories are inherently incomplete. But we bridge this gap, and we show that natural proofs really fail because of this incompleteness due to recursive definitions, right? And we will look at some ways to bridge the gap. So before I begin, a reminder of classical results. First-order logic is undecidable, right? But admits sound and complete reasoning, right? It is a sound and complete procedure. But the question here we're asking is first-order logic complete when we do systematic term instantiation, okay? The second is validity of first-order logic is RE, of course, but satisfiability is not. And when you add recursive definitions, you cannot express least fixed points or recursive definitions in first-order logic. And in fact, there is no sound and complete procedure for first-order logic with LFP. Okay. Okay, so here's the simplest setting is if you have first-order logic, no recursive definitions, no background theories, then we proceed in this refutation-based way. We take the formula, we negate it and show unsatisfiability, right? We scolamize by removing all the existential quantification, replacing them with functions. And then let's say we want to show, this is the term instantiation, we start with the formula, and every time we instantiate using all the universally quantified formulas, we look at the terms that are in the formulae in the previous level and instantiate these universally quantified formulas using those terms. And we can show that this is complete, right? This formula is unsatisfiable if and only if there is an I such that at the xith level you have completeness. Okay, so the second one, which is the main result, is to have first-order logic with background theories. And there's a very specific combination, which we call uninterpreted combination of theories. The idea is that you have several theories, T1 through Tn, and they are of different sorts, and they're disjoint sorts. And you have a foreground theory, which is disjoint from the background theories, background sorts, right? And the idea is that you have quantification over the foreground sort in the beginning, followed by alpha, and alpha can now have quantification of the background sorts, right? And these theories can be arbitrary, right? And we're going to be theory agnostic. We're not going to actually look at the theories or the axiomatizations. We're going to just do quantify instantiation over the foreground theory only, right? And so that's why the universal quantification is first over the foreground sort. So if we take such a formula, if I do quantify instantiation on the foreground variables, it's similarly defined. Every time in every step, I look at the quantified variables here and instantiate them using terms of type T0, right? And the resulting formulas will have quantification only over the background theories, right? And so we'll reduce reasoning to the background theories. And the question is term instantiation complete in this case, right? And it turns out it's not. There are simple examples that demonstrate that you cannot, this is not complete. Okay? And so here's the main technical result is that there is a fragment for which you get completeness, right? And this fragment is called the safe fragment. And the formula is safe if all subterms of sort T0 are guarded, where guarded means that you cannot have a term that refers to the foreground sort that involves universally quantified variables of background sorts, okay, which is a mouthful. So the intuition is that you cannot kind of look at the background sort, quantify over this, and then take a function and come here to the foreground sort, right? If you don't have that kind of terms, then it turns out that this instantiation is complete. And two simple ways of meeting this constraint are, one is to not have any functions from the background to the foreground, then obviously this condition is met. Or you could say there is no explicit universal quantification allowed on the background sorts, and that will also make it fall into this. Okay, so that's our main theorem, is that if you have the safety condition, then quantify instantiation is complete, right? And now I'm going to look at ramifications of this theorem, right? What this theorem actually gives us to understand natural proofs. Okay, the first one is that notice that if your formulas did not have quantification over the background sort, and it had only over the foreground sort, right? And these background theories were decidable, right? Then it turns out that this is a complete procedure, right? Because quantify instantiation gives you a complete procedure, because every time you get quantify free formulas, you can check whether they are decidable or not. And so you just repeat till unsat, do one more level of term instantiation, and check whether that's true using SMT solvers, right? So this shows this result shows that you can do a quantified combination of theories, right? Just like Nelson-Open, but Nelson-Open only admits quantify free theories. Here you're doing quantified theories, but crucially you're using the fact that the sorts are disjoint, unlike Nelson-Open, and that you will not get a decision procedure. You'll just get a recursively enumerable procedure. The second one is an understanding of natural proofs, why they work, and this is our understanding. So first is to see that quantify instantiation is when you do unfolding of a definition, notice that you're not paying any attention to the fact that it was a least fixed point, right? When you unfold this definition, the unfolding will be also valid if I did not have a least fixed point. I just had a fixed point, right? If I just said LF list is a function which satisfies this equation, right, then also the unfolding would be valid. So unfolding, which is the normal heuristic, completely ignores the least fixed point semantics of your definition. So we can think of natural proofs as two phases. One where you replace the least fixed point definitions by fixed point definitions, right? And if you do that, you're into first order logic without least fixed points, right? And the phase two is to do quantify instantiation that mimics unfolding recursive definitions. Okay. Now, it turns out that this second step here is actually complete, all right, because of our theorem. And the reason is that when you model heaps in the natural proof work, when we model heaps using this, what we do is we actually model heaps using a foreground theory. So locations and the heap are in the foreground, pointers are in the foreground, and data is stored as integers or whatever in the background. So functions always take you from the foreground to the background, right? And consequently, or heaplets take you from pairs of elements, locations here, maybe to sets here, right? And so it turns out that you can model this entirely using functions that go from foreground to background, and therefore it meets our restriction, and they are all safe formulas, and therefore they are complete, right? If you do instantiation, you will get completeness. In fact, it turns out that we don't typically need quantification over the background theory. You will need only existential quantification over the background theory. So both our restrictions that I mentioned, both of them actually met in the natural proof work. So phase 2 is actually complete, and phase 1 is always definitely going to have a semantic gap. You can't take a least fixed point and replace it with a fixed point and hope that nothing will go wrong. Okay? Things will go wrong. And remember, the first order logic with least fixed point has no complete procedure, whereas without least fixed points do have complete procedures. So let's look at when do natural proofs fail, right? Now, why couldn't we prove this simple statement saying if you concatenate a list segment with a list, you get with a disjoint list, you get a list, right? And the reason turns out to be phase 1, right? Because least fixed points, if you replace least fixed point with just fixed points, right, however clever you are, right, you can define linked lists using induction over natural numbers, where natural numbers are background theory. No matter how clever you are, it turns out that you'll always have non-standard models. So this is a segment where it'll declare x to y to be lseg x to y is true, even though it never reaches y, right? By declaring lseg x to y to be true all the time. You can build non-standard models like this, right? So the reason we could not prove them using term instantiation was that it wasn't a theorem, right? With respect to fixed point semantics, it wasn't a theorem, and the user therefore was not helping the system. It was actually giving new axioms, not lemmas. So these non-standard models crop up all the time. There are lots of uses of non-standard models in the paper. They're kind of non-intuitive, and I refer you to the paper for some literature involving arrays, which we also consider array property fragments there were some logics that were proved to be undecidable, but it turns out the undecidability proof was wrong because the authors did not consider non-standard models, right? So some of the one logic, which array property fragment with less than, strict less than, is not undecidable, right? But is actually an open problem now. Okay. So now let's turn to first order logic with least fixed points. We know we can't just replace them with fixed point definitions. So what do we do? How do we actually prove this? And the idea we have in the paper is to introduce what are called induction principles, that bridge this gap between least fixed point and fixed point semantics. Okay, so we explore strategies for introducing these principles systematically by looking at the formula that we want to prove, right? But no strategy can be complete, right? And we know that, right? But the idea is to stay within the FO framework so that completeness of term instantiation is something we'll get after we introduce these principles. So induction is not first order, right? So induction principles are not first order. So what we do here is actually introduce something of this form. Suppose R is a recursively defined definition, right? R is defined using rho. And we want to prove that R implies psi for every x. Then we introduce this induction principle, which basically says that if psi is a prefix point of rho, then R implies psi. Okay? So we look at the formula and rewrite it to this R implies psi form, and then introduce this. This is a valid formula in the FO plus LFP framework that we can just arbitrarily add, right? And this will actually help proving, bridging this gap and proving theorems on it. So it turns out that this is quite effective. All the axioms that we used, which we couldn't prove in the natural proof work for heaps, we took them and now did automatic induction principle discovery and showed that all of them are actually provable now, right? So this seems to be a very effective technique. There are slightly more general versions in the paper, but if you think about it, first order logic with least fixed point is actually as expressive as programs, okay? The whole, you can write the whole run of a program using first order logic with least fixed points. So this is actually also a way to generate invariance, right? And we have to see whether this is actually works well in practice for synthesizing invariance, loop invariance. So we come back to this understanding of natural proofs that phase one is inherently incomplete, right? By replacing LFP with fixed point definitions, you need to bridge the gap. But you can bridge this gap using some induction principles that we can discover and probably enlarge as time goes by. But phase two of the procedure is actually complete, right? And perhaps this is why, you know, things are so robust in practice. The one important thing is to ensure safety. You can easily define logics where things are unsafe, and then our theorems will not hold, right? So conclude. So there's some practice to theory, mostly, right? Is that to take heuristics that are based on quantifier instantiation and unfolding of recursive definitions and show that it's complete for this safe fragment of a multi-sorted, uninterpreted combination of theories. And there is some theory to practice as well here, because once we understood where the gap was, we were able to fill that gap by building these induction principles that could be used back in practice to get better procedures. And so we get a robust understanding of natural proofs. So safe first order logic with least fixed point seems like a powerful verification logic that seems to admit automation. Okay. There is some related work by Gay and Demura, which I did not talk much about related work. There is one work here which actually is very similar in spirit to our work, but they do not assume that the sorts are disjoint. And it turns out that you get very weak results if you do not assume sorts are disjoint. If you assume the sorts are the same, like Nelson-Oppen, you get very weak results, and it will not capture natural proofs as we do here. Okay, I'm done. Thank you.
So the first online question got lots of votes. How is this safe fragment better compared to the well-known stratified fragment where you disallow function cycles?
Yeah, so you do have cyclic things. You can have from the foreground to the foreground, you can have functions. So if you have a stratified logic, if you do quantified instantiation, it will terminate. Here it will not terminate, right? So you do have functions from the foreground to the foreground, and that's a big difference.
Are there anybody who wants to ask questions in the audience? Okay, the second online question: does the procedure of a quantified instantiation always terminate?
No. So for first order logic, in general, you cannot build something that terminates and is sound and complete as well, right? So it's undecidable, so it will not terminate. Yeah. So one thing I must emphasize is that in practice, you do the first few steps, and if it doesn't terminate, you give up. I mean, most of the valid formulas the heuristics are built because they work well in practice, and typically in a deterministic unfolding will actually give you the validity if the formula is valid. Yes.
Hi. So I have a question about the lemmas that you mentioned that you were able to prove with the induction principles. So if I understood correctly, you took these lemmas and you applied the induction principles. But really, when you have a piece of code, you need to invent this lemma. So do you think the induction principles can also work without?
So we have not experimented with actually taking just the VC and building the verification from that. So we have only proved that the lemmas are provable, right? And the lemmas were not provable before.
Okay, thanks, speaker again.